Okay. Okay, so my name is Steve Haynal, and I'd like to present a hobby project of mine. This is an open source software-defined amateur radio called the Hermes Lite. So this is for ham radio operators. It's a receiver and a transmitter. So the most novel part of this radio is that we've repurposed a cable modem IC. So anyone who has a cable modem at home, there's probably something like this in there. And it turns out that this makes a decent SDR. There's a 12-bit 80 megahertz A to D and D to A converter in there, and also integrated low noise amplifier. And so because this is a commodity part and because of the integration, it can significantly reduce the cost. So this is one of the goals of the project. This entire radio costs about just under $300 to purchase. This is what we call a direct down and up conversion radio. So it covers baseband frequencies only. So from the Nyquist-Shannon theory, we can cover about 0.1 to 38 megahertz. This is the the shortwave frequencies. It's different from other SDRs that you might know about, like the RTL SDR or the Lime SDR, which will cover a larger set of frequencies in that we don't have an analog mixer. That's where the direct down and up conversion go. We feed the signal directly into the A to D converter. Other SDRs will have an analog mixer that allows them to extend the frequency range, but this also adds some distortion and artifacts and noise. So since we're only interested in shortwave frequencies, we do this direct conversion. This is also a complete radio transceiver. So that means that we have some of the filtering that's required. We have some instrument quality RF preamp because we have a low power output and a full power output. We can use this as a vector network analyzer also. And we also have a 5-watt RF power amplifier. So this is more than the hundreds of milliwatts you would typically see from an SDR. And it's enough to be a QRP transceiver, which means a low power amateur radio transceiver. To go along with that 5-watt amplifier, we also have this switched RF filter board. And this is so that we meet the international regulations for harmonic suppression. So the amplifier will produce some harmonics, and we need to attenuate that with this board. We have 1 gigabit per second Ethernet. And this is so that the radio can be far away from the host computer. And finally, we use a Cyclone 4 25K logic element FPGA for most of the digital signal processing. So I'd like to just explain a little bit about how we use this radio. Now that you can send instant messages around the world over the internet, what's the point? Well, it's kind of a sport. We monitor space weather. We're at the low of an 11-year solar cycle right now, and then we choose the times and the frequencies we want to operate on so that we can bounce our radio signals off the ionosphere and communicate long distances. Here is a picture of one of the software packages we use with this radio, and we get a wide band view of an entire amateur radio band. This is the 40 meters band. And we can identify things that we couldn't before, like we can see household noise over here on the left. Here you see about 30 Morse code operators going there, and then there's a digital FT8, which is a new popular digital mode, the one that I like to use. Then we have single sideband voice communications, which is a technology since the 60s, and then on the very right you can actually see a shortwave broadcaster. So unlike some other SDRs, everything on the shortwave spectrum is very narrow band. We only have it from about 3 to 30 megahertz. So we're not interested in like large chunks of bandwidth, but we are interested in many receivers that are listening to small chunks of bandwidth. So here we have a piece of software that is running 8 receivers, and each of these receivers are listening to a different band in the amateur radio band in the shortwave spectrum. And in particular, this one is monitoring FT8, which is a digital mode created by a Nobel laureate from Princeton. He was doing radio astronomy, and he's also an amateur radio operator, and so he used a lot of these techniques that he used for filtering out noise to develop this communication mode. So it's a very low bit rate, 348 bits per second, but it's very tuned for noisy environments. And with that low bit rate, we can only send very short messages like our call sign, our location, and what your signal strength is. And all of these reports are captured on the internet. And so there's this site, PSK Reporter, and here's a map view of all the stations that I heard in the last 24 hours, and I just have a long wire antenna in my attic. So all continents except Africa and Antarctica. Africa is not too active. But I also, on transmitting, people in New Zealand and Japan and other parts of North America have heard me. Here's another visualization. We can visualize the whole entire HF spectrum. So this is from 0 to 38 megahertz, and you could see over on the left where the AM broadcasters are, and you can actually see some interesting things like my antenna has a better impedance match at certain frequencies, so you see these humps as you go up through the radio spectrum. So it provides a very new kind of view to a long-time hobby. So this is entirely open source, or as much as open source as we can make it. We still use the Quartus tools. The FPGA, Verilog, is in Verilog, and it was forked from another project, the OpenHP SDR project. This is one of the earliest open hardware projects there was, and they were one of the first to create an open hardware license, which is similar to GPL. There is no soft CPU in here, so we're doing everything by state machines. And some of the IP that might be interesting for people to reuse, it's not packaged nicely, but if you dig into it, you could dig them out. There is a small standalone UDP stack, which includes DHCP. So when I plug this in, it just gets an address from my DHCP server, and I could send UDP streams to and from this. And so that fits in less than 3,000 logic elements. It's could be something if you have tight space in your FPGA and you want Ethernet connectivity. We also have some high-performance NCOs, filters, and DSP on here that are written in Verilog. We're not relying on the vendor's IP for that. It was done with KiCad. So we have the schematics and PCB. It's a 4-layer board. We wanted to reduce costs. And all files, including the BOM and Gerber, are on GitHub. One of our focuses is we want to use a small batch assembly. So we want to be able to say, okay, 25 interested people can come together and they can create an order from a small batch assembly house in China. So we've been working with 2 of them, and we've had about over 75 units made by one. Homebrew people made about another 20, 30, and just this month we finished a collaboration with Maker Fabs, which specializes in open hardware, and they've sold 100 units. And so they're taking care of everything, the testing for us, manufacturer, fulfillment, which makes it very easy for a hobbyist to be able to get something like this out the door. We also do some co-simulation with MyHDL and Icarus Verilog. And so I wanted just to show you one of what we can do with that. Because it's Python, we have access to NumPy and SciPy, so that makes it very easy for us to look at things in the frequency domain, for instance. And so here we're looking at the output of our numerical controlled oscillator, and we want to make sure that, for all the frequencies, we don't have spurs that exceed a certain threshold. So here are the links. Everything's on GitHub. We have an active Google Groups with about 400 members, mainly amateur radio operators. And then we also have a main page here, which contains these links and other links that are relevant to this project. So thank you. I have this in the rear if anyone wants to take a look at the real unit.
Since we're not lighting fast, we can take questions if anyone has any.
Is there another revision in the works? And what would it include if there were?
This is actually revision 2.0, and nothing planned right away.
I'm curious if, with all the progress that's been made with the open hardware or open source FPGA toolchains, if you've looked at the Lattice ECP5 as a possible future option for, say, a 3.0 revision.
I did look at the ECP5 in the past. The original project that this came from was using Altera, so I kind of went with Altera for that reason. I don't know if I have enough motivation to change the FPGA at this point, but ECP5 is a good candidate, yeah.
Yeah. Anybody else?
Just on a related note, how big is your design? How much of the Cyclone 4 are you actually using at this point?
So it's about 90% utilized, and what we do is we can turn a knob which has the number of receivers. So we basically turn that knob up to as many receivers as we can. So currently we're at 4 receivers, so we could like put it in a smaller FPGA and have 2 receivers, or there's others that use larger FPGAs that have like 7 or 8 receivers.
For the digital modes, you mentioned FT8, and so do you support standard decoders for FT8, standard programs like AWJC, X, whatever, and do you support FT9?
So yeah, what I'm using is a WSJTX, and it was written by this retired Nobel laureate from Princeton, and it's well maintained, and it connects to software through like a virtual audio channel. So.
But the one you showed was different.
Yeah, that one actually does call WSJTX behind the scenes, kind of like a library.
All right then, let's thank our speaker.